So what have we done? We have looked at waves. We have looked at electromagnetic radiation, which behaves as waves. We have talked about the properties of that wave nature. Now we're ready to kind of change gears a little bit and talk about something called quantum theory. Okay, so we introduced that idea of quantum theory at the very beginning of this chapter. Now we're going to tie it into electromagnetic radiation. Okay, so we had this idea of Planck's theory, and I didn't really elaborate what was going on, which led him to come up with this idea of quanta. But what he did is he took a metal, solid metal, and he heated it up until it glowed, and it produced electromagnetic radiation. If you've ever been around an electric stove cooktop, you know you can turn it on and the burner gets bright and it starts glowing. Okay, so there's heat. When something gets heated up, it can get heated until it glows. All right. Then he started measuring the amount of electromagnetic radiation, or the amount of energy that was being emitted. And he examined various wavelengths. So he'd say, okay, I'm going to filter out everything else and I'm going to examine only this wavelength. Okay, so let's say he was looking at 380 nanometers. So he's looking at that wavelength. And he examined that wavelength and he measured the amount of energy that was emitted. And then he filtered out all the other light and he looked at another, say maybe 540 nanometers. So he's looking right here at this wavelength of light, and he made measurements of that energy. And he made very careful measurements at various wavelengths of what was emitted from that thing that was heated up. All right. What he saw, and I shouldn't talk about that yet, what he determined was where he measured at this wavelength or at this wavelength, where he measured the amount of energy was always related to that wavelength. So there were certain amounts of energy that was emitted at this wavelength, there were certain amounts of energy that were emitted at this wavelength, and he couldn't get them to always emit the same amount of energy. And that seemed kind of strange, because in the big world, you can have a little energy, you can have a lot of energy. What the wavelength is, it doesn't matter. It's just going to be a little to a lot, and any continuum in between. So this was a very unique idea. So it left the world of classical physics, as I talked about before. Planck, what he proposed with his ideas of what he measured to solve that problem, he assumed this, that atoms and molecules could only emit a discrete amount of energy. Didn't know why, but he says that's what's happening here. When it is glowing and it is emitting energy, it can only give off a certain amount of energy, and it could only give off multiples of that energy. And these little energy bundles that he called were a quantum of energy. Now this is the kind of a weird concept when we're talking about energy, because we're used to being able to have a continuum of energy. But it's not a foreign concept to us. We deal with quanta very often. For example, our money system is a quanta. The smallest bundle of money is a penny. So you can have something cost a penny, although nothing does anymore, okay? 2 pennies, 3 pennies, 4 pennies, $1.47, but you can't charge somebody $1.47 and 2/3, okay? We have the smallest bundle of money, which is a penny. I don't care what the gas stations say, they're not going to charge you 9/10 of a penny for a gallon, all right? So they always say it's, you know, $1.47 and 9/10, but that's just, don't even get me started on that. All right, so we've got this idea of quantum. Here's another example of a quanta, kittens, all right? A cat is going to have a litter of kittens, and the smallest bundle is 1 kitten. Could have 1 kitten, could have 2 kittens, it could have 3 kittens. You will never have a cat give birth to 2.5 kittens. At least I hope not, okay? So that would be a quanta of cat. All right, so here is the energy bundle. E equals h nu. Now we've seen nu before. Nu was our frequency. We talked about frequency before. So energy is E is the energy of just one quanta. He didn't know what was causing this. He just said this is the smallest bundle of energy, E. And it would be equal to h, which is, well, it's a constant named after him, okay? 6.63 or 6.626, all right, times 10 to the minus 34 joules times seconds. That is Planck's constant. Now, you do not have to memorize Planck's constant. Remember, when you take the test, there's a periodic table, and at the bottom of that periodic table are a bunch of constants. This is one of them. Now, you'll probably use it so many times that for a while it'll be stuck in your head, but when you take the test and you're freaking out, know that it's there. Okay, so the last one, of course, is our frequency, and our frequency of light emitted as far as units is going to be 1 over seconds. Okay, so if we take joules times seconds and 1 over seconds and multiply them, we will be left with a joule, which is the energy of this little bundle. Now, because Planck's constant is so tiny, this little energy bundle is a very tiny energy bundle. And eventually, but not yet, we'll do calculations using this equation. But right now, we're just concentrating on the fact that Planck did this study. He examined light at a certain wavelength, in other words, at a certain frequency, and he noticed that the light emitted from that thing at that wavelength or at that frequency was always a multiple of this energy here. Okay, it was always this energy or twice this energy or 400 times this energy or 5,000 times this energy, but it was never in between. It was always a multiple of this. Okay, so this led us to what we call the particle nature of light. So that's where we're journeying down now, is trying to understand the particle nature of light. So here's a typical science scenario. Somebody makes an observation, okay? They come up with an observation, they notice that this is true, this is the way it is every single time. Sometimes we base a law upon that, okay? But that is an observable fact. We note this, but it is not usually where we stop. If you're a scientist, the next thing you want to know is why. Now, Planck did not come up with the why. He just did the observation. He did careful studies to observe this phenomenon happening. He is the father of quantum theory, but he could not get to the point of understanding the why. The great mind of Einstein had to come along in order to kind of start giving us a why for what's going on. What Einstein would do is he would take Planck's work, and then he took something else called the photoelectric effect. And we're going to really examine this photoelectric effect. He took that work and he could explain what's going on. Why, when this thing glowed, was there an emission of energy that was always a multiple of E equals h times nu? So let's examine what's happening here. All right, so here is our apparatus. All right, let's zoom in on our apparatus. We have a metal plate. This metal plate is in a chamber, glass chamber that's evacuated. They've taken all the air out. It is hooked up with electrodes to a battery, and we have a meter here that can measure the current, okay, that's flowing through this wire. And here's what this experimental setup was. They would take light of a certain frequency and strike that metal plate. Sometimes, under some conditions, the electrons would be emitted from that plate and would be attracted to the positive terminal and complete a circuit, and you could measure that current. Okay? So electrons, which are negatively charged, would be attracted to the positive electrode. It's hooked up to this battery, so we have a positive and a negative electrode. Now let's zoom in on this surface a little bit, okay? So somehow that light is hitting this metal surface, and what's in there? Well, there's nuclei of the metal and the electrons buzzing around, and this sea of electrons that can flow around in here. Sometimes that light is like a soccer player who kicks a soccer ball and is able to kick it out, all right? Kick an electron or soccer ball off that metal surface. Now sometimes this light, when it strikes the surface, doesn't kick anything off, and sometimes it does. All right, so that's the setup. Here is what they expected, because they knew that light, even light that is got long wavelengths, they knew that light could be really intense, and they thought that if the light was intense enough, it didn't matter what the frequency was, you could eject an electron. What is intensity associated with? Well, intensity is associated with amplitude, okay? And we know the higher the amplitude, the more energy it attracts. So if we have really, really intense light, it carries a lot of energy, and you would expect a lot of energy could kick off that electron. And that is not what they found, okay? Here is what they found instead. They found that there was some frequency of light, that it did not matter how intense it was. If you were below that frequency, no electrons would get ejected. Okay? So this would be like, you know, a soccer player going up, kicking the soccer ball, and they just don't have enough energy to get it to go anywhere. Okay? Seems unfathomable with a soccer ball, but that's what's happening here. And if they made that light extremely intense, so it's certain frequency, but it's really bright, it still would not eject any electrons. What else did they find? The next thing that they found was if you could get them to come off, okay? So once they were able to be ejected, increasing the intensity would increase the number of electrons that came off. That was the next thing they found out. So if they could increase the intensity, which up to this point, what did that look like? Well, that would look like, you know, a higher wavelength in their mind. I mean, a higher amplitude in their mind. They're increasing the intensity, and that would cause more electrons to come off. They also found that if they increased the frequency of light, okay? So what does that mean? If we're increasing the frequency of light, it's a smaller wavelength. Okay, they increase the frequency. Not changing the intensity, they're just changing the frequency. This would cause the electrons to be ejected with more kinetic energy. So as the wavelength got smaller, okay, so I have a certain wavelength here. If it were to get smaller, so there's a smaller wavelength, when it hit the surface, it would eject that electron with even more kinetic energy. It'd be moving faster. Okay, coming off that at greater speeds. If the wavelength was a little longer, okay, so I will do a little longer, but it's still long enough to eject an electron, the electron would come off, but it would come off with less speed, with less kinetic energy. So those are all the things they found. This was what we called the photoelectric effect. Photo for light coming in, all right, so light's coming in. Photoelectric because we have electrons coming out and completing a circuit, and we're being able to measure the electricity. So we're going to re-emphasize what they found, all right? At some frequency, which was longer wavelengths, they found that if they struck the metal surface, no electrons would come off, even if it was very intense light. They found that there was some minimum frequency or short enough wavelength so that you could get an electron come off. And once you had an electron come off, if it got more and more intense, you get more and more electrons come off. And then the third thing is, when the wavelength got shorter and shorter, the frequency got higher and higher, then when the electrons came off, they came off with greater and greater speeds, or kinetic energy. Okay, so that's what they discovered. This is still not explaining quantum theory. This is still not explaining why when something glows it gives off discrete bundles of energy. So Einstein's going to tie it all together here. So here is the explanation, okay? He's explaining the photoelectric effect. He said this is what's happening. Light is not just a wave. It also exists as particles, okay? And he called these particles, photons. Okay, which you've heard of, most people have, photons. These are the little particles of light, okay? And each one of those photons have this much energy, Planck's energy. Energy equals h nu. Each photon, if it has enough energy, Okay, now what kind of energy? Its energy is associated with its frequency. Each photon, if it has enough energy, is the soccer player, and it can kick an electron off that metal surface. Okay? If that photon has a higher and higher in frequency, it has a bigger energy. Okay, so let's write that down. Whoops. Get that, go in the right direction. There we go. So if as the frequency goes up, the energy of that photon is going to go up. So if the frequency is going up, the energy goes up. So what does that mean in terms of our soccer player? Well, the soccer player is stronger, and it has more energy in its kick, and it could kick that electron, that soccer ball, even harder, and it's going to cause it to fly off much more rapidly. So we've got this correlation between a photon and its ability to kick an electron off. If the frequency is really low, okay, the energy of that photon is really low. And we've got somebody who is so weak that they can't even kick the soccer ball off, okay? Maybe the soccer ball is stuck with Velcro and it hits and it doesn't do anything. So that electron has got an attraction to the surface. And there are some photons that can't make it move. Those are low frequency, low energy photons. We have got frequencies that are soccer balls that are still stuck, but enough strength that it can kick it and it can kind of move. And then you've got a photon that's like a really strong person that can kick it and it can really go zooming. But each photon can only move one electron. What happens if you get the light more intense? Well, a greater intensity of light means you've got a lot more photons coming in. And each photon has a capacity of kicking one electron off. So it'd be like a whole bunch of soccer players. Each one can only kick one soccer ball at a time. Okay? Now, this is what some terms that are associated with this. Okay? We call this the binding energy. How strong is that electron held to the surface? It's called binding energy. It'd be like if you got your soccer ball and it's got Velcro all over it, how tightly is it held to that Velcro surface? Okay, that's the binding energy. How tight is it being held? And we use that to symbolize the binding energy. So the more intense the light, the more photons are striking the plate. And each photon that strikes a plate will use some of its energy to get the electron off. That's the binding energy. It will use the rest of the energy to give that electron energy. So what we see on the left is the photon's energy. That's the energy of the light. You think about that as the soccer player kicking the soccer ball. Okay? The higher the energy of the photon, the more energy it strikes. There is some of that energy that is going to give that photon an ability to leave the surface, and the rest of it is going to give that, sorry, I said photon, give that electron the ability to leave the surface, and the rest of it is going to give that some kinetic energy. All right, so now what does that leave us with? We know two things about light. We know that light has a wave nature. We see that wave nature. We see that light when it passes through two slits will have this interference pattern that is a telltale sign that we have waves. We also have this idea of the photoelectric effect. The photoelectric effect says that light doesn't just have this this wave nature and this diffraction pattern that's so distinctive of a wave, but it also has things that can only be explained by the fact that they're particles. And from here on, when we think about intense light, we're not going to think about high amplitude. What we're going to think about if it's intense is it's more photons, more particles coming out. So when you brighten a light, if you've got a dimmer switch on your light, when you've got it dimmed down, okay, it's not that the waves are coming out with little amplitude, it's just fewer photons coming out. And when you crank it up and you make it brighter, as it gets brighter, you're being hit with more photons. But each one of those photons have got the same wavelengths, the same frequencies associated with them. Okay, that's the end of this lesson.